So the next talk is on the real-time extension, as far as I remember, on our hypervectors. So next talk is on hypervectors.
Hello, everyone, and thank you for joining this session. My name is Rocco Martino, and I'm a first-year PhD candidate at Sapienza University of Rome. And today, I'll be presenting my work on a new RISC-V instruction set extension with hardware acceleration for hyperdimensional computing. We will briefly introduce the hyperdimensional computing paradigm and explain which are the motivation behind the choice to realize a dedicated instruction set extension for this paradigm. And we will see the proposed architecture that consists in an hardware accelerator integrated into the RISC-V core, which is the Klessydra core. And finally, I give you some results from the point of view of hardware resource usage and speed-up performance. This work is being done by all the members of the Digital VLSI Circuit and System Research Group, led by Professor Mauro Olivieri. So let's start with a quick introduction to hyperdimensional computing. We are talking about a well-established computing paradigm that encodes information through distributed and high-dimensional hypervector, or what we call hypervector. And the mathematical space where these hypervectors are manipulated is characterized by a very small set of arithmetic operations. The main one are the binding, which is more or less like a product, bundling, which is more or less like a sum, the permutation, which is a classic cyclic shift of a vector, and the similarity, which is not properly an operation, but is a tool for compare hypervector. And however, by appropriately combining this operation, it's possible to build computing models that are able to perform learning tasks, such as regression, clustering, or classification. And without diving into the mathematical details of the paradigm, what really matters for us today is that many of these computing models come with a set of very compelling properties. And they are, for example, they are computationally and energy efficient, they are highly scalable, they present a really good resilience against noise and hardware faults, and they can learn from a bunch of examples, and they present an extreme parallelism degree. And all these properties make hyperdimensional computing not only ideal for implementing AI on resource-constrained system, but make it also a perfect candidate for hardware acceleration. Of course, the potential of this paradigm hasn't gone unnoticed, and many people in the research community, in the scientific community, have developed their own hardware accelerator, and several of them are strongly efficient. But as we went through the literature, we started to notice that many of them had some common limitation. First, they have a fixed learning pipeline, meaning that they cannot be reused for a learning task different from the one they were originally designed for. They are tightly coupled to the data set and often accelerate composite operation of the paradigm. And they work with fixed length and fixed type hypervectors. And what does it mean in practice is that algorithm developers are left with low flexibility, and they cannot easily experiment with new learning strategies, or they cannot easily adapt an existing hardware accelerator on their own datasets. So we asked ourselves, how can we bring flexibility back to algorithm developers without asking them to realize that custom design every time. And that's where RISC-V come in, because its modular and open nature make it the perfect foundation for a general purpose hyperdimensional computing accelerator, one that lives inside a processor and evolves with the software. So instead of building yet another fixed function standalone accelerator, we directly integrate into a RISC-V processor a reconfigurable hardware accelerator, which we call HDCU, to optimize the execution time of HDC task. And specifically, we integrate our design into the execution stage of Klessydra-T03 core, which is a 32-bit RISC-V open source 4-stage pipelined processor developed in the Digital Bullseye laboratory at Sapienza University. And this is a core signal-to-signal compatible with the PULP platform developed by ATH of Zurich. And since the HDCU was integrated into the execution stage of the processor, of the core, and it works in parallel with the load store unit and with the arithmetic logic unit, it behaves more like a coprocessor than a traditional hardware accelerator. But let's have a look at the main feature of the design, of our design. Obviously, one of the biggest strengths of RISC-V is its open and extensible instruction set architecture, and we took full advantage of that. To control the accelerator, we designed a custom instruction set extension that introduced dedicated instruction to support all the fundamental arithmetic operation used in hyperdimensional computing. And these instructions are fully integrated into the GCC toolchain and are exposed as a simple intrinsic C function in C, making them easily accessible from high-level code. And thanks to this modular design, developers can implement virtually any HDC algorithm just by combining these instructions without the need to worry about the low-level hardware details. And for each instruction in our custom extension, the accelerator includes a dedicated and highly optimized functional unit, one for each fundamental hyperdimensional computing operation, for a total of 6 units. And the level of parallelism for these units can be configured at synthesis time through the SIMD parameter, allowing us to balance execution speed and hardware resource usage. Now, regardless the parallelism level, the accelerator uses hardware loops to process hypervector efficiently, and this means that once the instruction is fetched, the corresponding unit keeps working until the entire hypervector is processed without the need to refetch the same instruction over and over. And this is a key advantage because it allows the system to handle hypervector of arbitrary size without stalling the pipeline or overloading the main processor. And to avoid bottlenecks, all hyperdimensional computing operations are executed directly on local memory, which we call scratchpad memories, without continuous transfer to and from the main memory of the core. And the transfer are handled explicitly only when needed through 2 more dedicated instructions, which are the HVMem store and the HVMem load. And the table in the slides summarize all the key configuration parameters of our accelerator. Most parameters, such as memory size, memory count, and hardware parallelism, are set at synthesis time to adapt the design to a target constraint. And in contrast, hypervector size and number of classes, if we are facing a classification problem, can be synthesized, can be set at runtime by the programmer by using the CSR, the current status registry of the core. And this configuration is applied once at the beginning of the C program and give all the needed information to accelerator to control the hardware loops. And another important feature is the ability to selectively enable or disable a functional unit based on the application. And for example, if we if the application doesn't need the permutation unit, we can disable and save area and power consumption. And this dual flexibility, hardware and software, can clearly distinguish our design from application-specific accelerator found in the literature. And it enables a versatile and efficient architecture adaptable to a wide range of learning tasks. So let's see on some hardware results. So to validate our design, we implement the Klessydra-T03 with the Hyperdimensional Computing unit on a FPGA board. And as we can see from the top table, the hardware resource required by the design is very low. And this is because Klessydra is a RISC-V core designed for IoT. And the core required circa 4,000 lookup table, meanwhile the HDCU only 1,000 in the minimal configuration, so with the lower hardware parallelism. And as we can see in the bottom table, we also evaluate how the hardware resource usage scales with the increasing SIM value. And this allows us to trade off between the execution time and the resource usage. Now, let's look at some performance results. First, let me clarify that we measured the performance of our accelerator using the speedup factor. And this factor is computed as the ratio between the number of clock cycles required by Klessydra to execute an hyperdimensional computing operation purely in software and the number of clock cycles required by Klessydra to perform the same operation by using the accelerator. And on the right side, we have 6 different graphs, each corresponding to one of the functional units implemented in the accelerator. And let's take a closer look to one of these. So the speedup factor was computed varying the hardware parallelism level, and on x-axis we have the hypervector size, and on y-axis we have the speedup factor, and each colored curve represents the various levels of hardware parallelism. And this graph represents the speedup factor of the bundling operation, and we have an amazing speedup factor starting from 23 times to 2,600 times. That means that we are going more than 2,000 times faster than the purely software execution. So, to wrap up, in this work we introduce the HDCU, which is a configurable and general purpose coprocessor designed to accelerate the arithmetic operation at the core, that stand at the core of the hyperdimensional computing paradigm. We build this architecture as an extension of the RISC-V instruction set and enabling a clean and accessible interface for developers through custom instruction and compiler support. And we then validate our design on an FPGA, and the results show not only significant speed up across all HDC operations, but also excellent scalability thanks to the configurability of both memory and parallelism. So thank you for the attention, and feel free to ask a question.
Okay, no need to be shy. So any questions on this one? Well, we have one.
Greetings. Excellent work, I'd say. Did you compare your work with the performance against the standard RISC-V vector extension?
Not yet. Or we compare our work with existing RISC-V processor that accelerate some specific hyperdimensional computing operation, but they are a composite operation. Okay, so meanwhile we accelerate the basic operation that stand at the basic operation of this paradigm. They try to accelerate for example, the encoding operation of hyperdimensional computing. So the comparison will not be so possible. Okay, but we try to compare our performance with another existing accelerator for vector operations, and obviously it performs better because we have a specialized functional unit to perform the operation of hyperdimensional computing. So the speed up is bigger, okay, is higher. And so, this is.
Thank you.
Welcome.
Thank you, great presentation. I wanted to ask regarding the hypervector size. Yeah. If you would make a very large hypervector, how would the graph look for the specific operation? Would the curve taper off at some point, or will it continue rising?
It obviously, let's say, saturate because the transferring from scratchpad memory is limited by the scratchpad memory interface. So we will see that the brown cards will behave like the other one. Okay, so if we will extend the x-axis, we will see a saturation.
Thank you.
So, thank you for your questions and thank you for this research presentation.